Beyond Neptune, the solar system does not end. It transforms into something stranger. Past the last giant planet lies a region so vast it dwarfs the entire distance from the Sun to Neptune, a frozen frontier stretching billions of miles into darkness, home to thousands of icy worlds and ancient relics older than any planet you have ever learned about. This is the Kuiper Belt. The reason most people have never pictured it is not because it is hidden from telescopes, it is because it shatters the neat, tidy map of the solar system that everyone carries in their mind. What lies beyond Neptune is not emptiness. It is a structured outer province of our own home that quietly makes everything you thought you knew about the solar system incomplete. If you want to discover why the real frontier of our solar system rewrites everything you thought you knew about home, go ahead and hit that like button and subscribe. It really helps the channel and it means more than you know. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, get yourself comfortable. Let's begin. Neptune was never a wall, it was always a doorway. For most of the 20th century, the eighth planet sat at the edge of every solar system diagram, like a period at the end of a sentence. Textbooks drew the last blue circle, labelled it Neptune, and let the page fade to black. The implication was clear. Beyond that final giant planet, there was nothing worth drawing. The solar system ended and interstellar space began. This was not a fringe belief held by amateurs. It was the working assumption of professional astronomy for decades. And it was profoundly, consequentially wrong. The mistake was understandable. Neptune orbits approximately 30 astronomical units from the Sun, roughly 2.8 billion miles. At that distance, sunlight is around 900 times dimmer than what reaches Earth. Temperatures plunge below -200 degrees Celsius. Any objects beyond Neptune would be small, dark, and impossibly faint, reflecting almost no light back toward telescopes on Earth. If something existed out there, it hid so effectively that astronomers had no practical way to detect it, with the technology available through most of the 20th century. But the absence of evidence was mistaken for evidence of absence. Scientists looked past Neptune, saw nothing, and concluded nothing was there. The solar system had a tidy architecture. 4 rocky inner planets, 4 gas and ice giants, and then the void, clean, organized, complete, except it was not complete, not even close. The first cracks in this assumption appeared not through direct observation, but through a problem involving comets. Comets are among the most ancient and fragile objects in the solar system. They are loose aggregations of ice, dust, and frozen gases that heat up and develop glowing tails when they approach the Sun. Scientists had long recognized 2 broad categories. Long-period comets, which take thousands or even millions of years to complete a single orbit, arrive from every direction and at steep angles. Their source was identified in the mid-20th century by the Dutch astronomer Jan Oort, who proposed a vast, spherical cloud of icy bodies surrounding the solar system at distances of roughly 2,000 to 100,000 astronomical units. The Oort cloud, as it became known, explained these unpredictable long-period visitors well enough. But there was a second category that the Oort cloud could not explain. Short-period comets complete their orbits in less than 200 years, often much less. Comet Halley returns roughly every 76 years. Comet Enku orbits in just over 3 years. These comets share a distinctive feature. They travel in relatively low inclination orbits, close to the same flat plane where the planets orbit. They do not arrive from random angles like long-period comets. They come in along the ecliptic, as if they originated from a disc-shaped source, not a sphere. This was a critical clue. If short-period comets came from the spherical Oort cloud, their orbits should tilt in every direction. But they do not. They cluster near the planetary plane. Something disc-shaped, relatively close, and packed with icy material had to be feeding them into the inner solar system. Something beyond Neptune, but much closer than the Oort cloud. The idea that a belt of icy bodies might exist beyond Neptune did not emerge overnight. It grew slowly through the work of several researchers who recognized the same logical gap. In 1943, the Irish astronomer and engineer Kenneth Edgeworth published a paper arguing that the solar system's original cloud of material could not have simply stopped at the orbit of Neptune. The protoplanetary disk that formed the planets must have extended farther out. But at those distances, material was too thinly spread and orbital periods too long for large planets to form. Instead, Edgeworth proposed, the outer disk would have remained as a vast population of small, unconsolidated bodies, a reservoir of frozen debris stretching into the dark. 8 years later, the Dutch-American planetary scientist Gerard Kuiper independently proposed a similar idea. In 1951, Kuiper suggested that a belt of small icy objects should exist beyond Neptune, though he believed Pluto's gravitational influence might have scattered most of them away over time. History would attach his name to the belt, despite the fact that Edgeworth made a comparable prediction earlier, and despite the fact that Kuiper himself was uncertain about whether the belt had survived to the present day. The most consequential theoretical argument came in 1980 from the Uruguayan astronomer Julio O. Ángel Fernández. While working on the dynamics of cometary orbits, Fernández demonstrated mathematically that the Oort cloud alone could not supply short-period comets at the rate they are observed. The numbers did not work. Comets burn out. Each time a comet passes close to the Sun, it loses material. After a few hundred or a few thousand orbits, a comet either disintegrates completely or develops a thick crust that seals in its remaining volatiles, turning it into a dead, inert nucleus. Short-period comets have relatively brief lifespans compared to the age of the solar system. If they have been burning out for billions of years, new ones must constantly be entering the inner solar system from some external source. Fernández calculated that a trans-Neptunian belt of icy bodies, orbiting at roughly 35 to 50 astronomical units from the Sun, provide exactly the right supply rate. This belt would act as a feeder zone. Occasionally, gravitational interactions with Neptune would nudge an object inward, sending it on a trajectory that gradually evolved into a short-period cometary orbit. The belt did not need to be dense, it just needed to exist. And it needed to be disk-shaped, which naturally explained why short-period comets arrive along the ecliptic. Computer simulations by Martin Duncan, Tom Quinn, and Scott Tremaine in the late 1980s confirmed Fernández's reasoning. Their models showed that a flat belt beyond Neptune could reproduce the observed population of short-period comets with remarkable accuracy, while the spherical Oort cloud could not. The evidence was now pointing strongly toward a trans-Neptunian disk of icy bodies. The theoretical case was becoming difficult to ignore, but proving it required finding one. This turned out to be extraordinarily hard. At such extreme distances, even the largest trans-Neptunian bodies measure only a few hundred miles across and shine so feebly that they appear as nothing more than faint specks, barely distinguishable from background noise in telescope images. In the 1980s, detecting them demanded long exposures with sensitive charge-coupled device cameras on large telescopes, and even then, success was not guaranteed. David Jewett and Jane Liu began their search in 1987. David Jewett, a British-born astronomer working at the University of Hawaii, and Liu, a Vietnamese-born astronomer who had studied at Stanford and the Massachusetts Institute of Technology, shared a conviction that the space beyond Neptune could not be as empty as conventional wisdom claimed. They understood the theoretical arguments and knew the cometary supply problem demanded a solution. They decided to look. What followed was 5 years of painstaking observation. Night after night, they pointed telescopes at patches of sky near the ecliptic, took long exposure images, then compared frames taken hours or days apart to look for anything that had moved. A distant Kuiper Belt object would shift its position very slowly against the background stars, perhaps only an arc-second or two per hour, but any motion at all would distinguish a solar system body from a fixed star. The difficulty was immense. Every frame contained thousands of faint points. Cosmic ray hits, detector noise, faint asteroids and background galaxies all created false signals. Jewett and Liu had to eliminate each one. They searched through approximately 60 square degrees of sky, examining tens of thousands of candidate detections over 5 years. They found nothing in the first 4 years. Funding was difficult to justify for a search targeting objects that might not exist. Colleagues were skeptical. The project risked becoming an expensive confirmation that the outer solar system really was empty. Then, on August 30th, 1992, using the University of Hawaii's 2.2-meter telescope on Mauna Kea, Jewett and Liu found it. A faint point of light, magnitude 23, roughly 4 million times too faint for the human eye, was moving at the right speed and in the right direction to be a distant solar system body orbiting well beyond Neptune. Follow-up observations confirmed the discovery. The object was orbiting at approximately 44 astronomical units from the Sun, with a nearly circular low-inclination orbit. It was small, probably around 60 to 120 miles across, and it was red in colour, exactly the kind of icy, primitive body that theorists had predicted. The object received the provisional designation 1992 QB1. It would later be formally named Albion. And it changed everything. Albion was not Pluto. Pluto had been discovered in 1930 and had spent 6 decades as a lonely oddity at the solar system's edge, the only known object beyond Neptune, apart from a handful of comets. Scientists had always treated Pluto as a special case, an anomaly, perhaps a wayward moon escaped from Neptune's gravity. Nobody thought of Pluto as a member of a population because no population had been found. Albion shattered that isolation. If one small body could be found at 44 astronomical units, others almost certainly existed. The discovery immediately validated the theoretical predictions of Edgeworth, Kuiper, and Fernandez. Within months, additional searches turned up more objects orbiting in the same region. By the end of 1993, half a dozen trans-Neptunian bodies had been confirmed. By the mid-1990s, the count was climbing rapidly. By 2000, it had passed several hundred. By the early 2020s, astronomers had catalogued well over 3,000 Kuiper Belt objects, and the estimated total population of bodies larger than roughly 60 miles across exceeded 100,000. The emptiness beyond Neptune was never empty. It was full. It had always been full. Humanity just lacked the instruments to see what was there. What the telescopes revealed was not a random scattering of debris. The Kuiper Belt has structure. It has shape, boundaries, and internal organization that reflect billions of years of gravitational evolution. The belt occupies a thick, donut-shaped region of space stretching from approximately 30 astronomical units near Neptune's orbit, out to roughly 50 astronomical units from the Sun. That span covers about 20 astronomical units of radial distance, but the belt is not flat like a compact ring. It has significant vertical thickness, with objects scattered above and below the plane of the solar system by varying degrees depending on their orbital histories. Some Kuiper Belt objects travel on orbits tilted just a few degrees from the ecliptic. Others are inclined by 20, 30, or even 40 degrees, arcing high above and below the planetary plane in long, looping paths. To grasp the scale, consider that the entire distance from the Sun to Neptune, the span that contains every planet, every asteroid, and every spacecraft humanity has ever launched, measures about 30 astronomical units. The Kuiper Belt, from its inner edge near Neptune to its outer boundary at roughly 50 astronomical units, spans another 20 astronomical units beyond that. This means the belt alone covers 2/3 of the distance from the Sun to Neptune in additional radial extent, and this is just the main belt. The scattered disk population associated with it extends far beyond 50 astronomical units, with some objects reaching orbits that carry them hundreds of astronomical units from the Sun. In terms of sheer volume, the Kuiper Belt is enormous. NASA describes it as roughly 20 times wider than the asteroid belt between Mars and Jupiter, and between 20 and 200 times more massive. The asteroid belt, despite its name, is actually quite sparse. If you gathered every asteroid in it into a single body, you would get something significantly less massive than Earth's moon. The Kuiper Belt contains far more material. Estimates of its total mass vary, but it likely holds somewhere between a few hundredths and roughly 1/10 of Earth's mass, modest by planetary standards, but vastly more than the asteroid belt. And that mass is distributed across a volume of space so large that individual objects are separated by enormous distances. The belt is dense in population but not in spacing. Trillions of cubic miles of cold vacuum lie between neighbouring worlds. If you could somehow stand on the surface of a Kuiper Belt object at 45 astronomical units from the Sun, the experience would be alien beyond anything the inner solar system can prepare you for. The Sun would still be visible, but it would no longer look like the Sun you know. It would appear as a brilliant point of light, intensely bright compared to the surrounding stars, yet no larger than a sharp pinprick, roughly 2,000 times dimmer than the sunlight that falls on Earth. You could stare directly at it without discomfort. It would cast light, but not warmth. At that distance, the solar energy reaching each square meter of surface is less than 1/2000th of what Earth receives. Noon on a Kuiper Belt object is darker than the deepest twilight on Earth. The temperature surrounding you would hover around -230 degrees Celsius, cold enough that nitrogen, which makes up most of the air you breathe, would freeze into solid ice on the ground beneath your feet. Methane would be a frozen mineral. Carbon monoxide would be a frost. Even some noble gases that exist as invisible vapors on Earth would condense into liquids or solids at these temperatures. The familiar chemistry of the inner solar system, liquid water, gaseous atmospheres, weather systems driven by solar heating does not operate here. Matter behaves differently. Water ice, the most common substance on these worlds, is as hard and rigid as bedrock. It does not melt, it does not flow, it fractures like stone under stress. The building material of the Kuiper Belt is rock-hard ice, in a vacuum so cold that the boundary between geology and cryogenics dissolves entirely. This is the physical reality of the frontier. Not empty space, not a blank margin on a map. A real environment with real conditions so extreme that the familiar rules of planetary science begin to bend. This was the realization that took decades to settle into the scientific imagination. Beyond Neptune, the solar system does not thin out into a final scattering of stray rocks. It opens into a substantial, structured, physically massive region, a frozen outer province, occupying a significant fraction of the solar system's total extent. The Kuiper Belt is not an afterthought appended to the edge of the planetary system. It is a major architectural component in its own right. The emotional and conceptual difficulty of absorbing this fact helps explain why the belt remained invisible for so long, not just to telescopes, but to the human imagination. People had internalized a mental map of the solar system that stopped at Neptune. Adding a massive outer region beyond the last giant planet required not just new data, but a wholesale restructuring of how the solar system was imagined. It was not that a few extra rocks had been found. It was that the solar system turned out to be a fundamentally different shape than everyone had been taught. Think about what the discovery meant in practical terms. Before 1992, every model, every textbook diagram, every classroom poster depicted a solar system that terminated at Neptune, perhaps with a small annotation for lonely Pluto drifting beyond. After 1992, that picture was incomplete in a way that could not be fixed with a minor update. You could not simply add a few dots beyond Neptune and call it corrected. The Kuiper Belt demanded a reconceptualization of the outer solar system as a region with its own geography, its own population dynamics, and its own relationship to the rest of the planetary system. The speed at which discoveries accumulated after Albion underscored how fundamentally the old picture had failed. It was not as if the objects were barely there, hovering at the edge of detectability. Once astronomers knew where to look and had the right instruments, they found Kuiper Belt objects in abundance. The belt had always been rich. Only the blindness of insufficient technology and insufficient imagination had kept it hidden. By the early 2000s, surveys had revealed enough objects to begin mapping the belt's internal structure. Astronomers found that the population was not uniform. Objects clustered into distinct dynamical families based on their orbital properties, their distances, their eccentricities, their inclinations, and crucially, their relationships to Neptune's gravity. This was not the behavior of random debris. It was the signature of organized, long-term gravitational architecture. Some objects occupied nearly circular, low-inclination orbits in a narrow band between approximately 42 and 47 astronomical units. These became known as the cold classical belt, the quietest, most pristine population, thought to have formed roughly in place and survived for over 4 billion years with minimal disturbance. Their name refers not to temperature but to their dynamically calm orbits. These objects are the undisturbed fossils of the solar system's original outer disk. Other objects travelled on more excited orbits, higher eccentricities, higher inclinations, suggesting they had been gravitationally disturbed at some point in the past. These form the hot classical belt, a population that overlaps in space with the cold classicals but differs profoundly in orbital character. The hot population likely arrived at its current location through gravitational scattering during the early solar system's chaotic rearrangement, rather than forming peacefully in place. Then there were objects locked into precise orbital resonances with Neptune. These resonant populations offered some of the most compelling evidence that the belt structure was not random but sculpted. And the sculptor was the giant planet sitting at the belt's inner edge. Every layer of data revealed more complexity. The belt was not a simple ring of ice. It was a structured, multi-layered, gravitationally organized region with distinct neighborhoods, different histories, and populations that recorded billions of years of dynamical evolution. And all of it had been hiding in plain darkness, just beyond the last planet anyone bothered to look past. The most stunning detail was how old the evidence was. Comets had been arriving from this region for as long as humans had watched the sky. Every short-period comet that blazed across ancient skies was a messenger from the Kuiper Belt, a piece of the frozen frontier delivered to the inner solar system by Neptune's gravitational nudges. The evidence had been streaking overhead for millennia. Nobody recognized where it was coming from because nobody believed the source existed. By the early 21st century, the Kuiper Belt had gone from a theoretical prediction to a confirmed observational reality containing thousands of known objects and an estimated population of hundreds of thousands more. Pluto, the lonely wanderer that had spent 70 years as the solar system's outermost oddity, was suddenly surrounded by neighbours. It was no longer an anomaly. It was the largest known member of a vast icy community. But knowing the belt existed was only the beginning. The next question was far more unsettling. Who lives there? What kinds of worlds populate this frozen province? And what do they reveal about the true character of the outer solar system? The frontier had been found. Now it was time to meet its residents. Pluto was never an outcast. It was a king without a known kingdom. For more than 6 decades after its discovery in 1930, Pluto existed in the scientific imagination as a solitary oddity. It was too small to be a proper planet, too distant to study in detail, and too peculiar in its orbit to fit neatly into any category. It crossed inside Neptune's orbit for 20 years out of every 248-year trip around the Sun. It was tilted 17 degrees off the ecliptic, rising far above and below the plane where the other planets travel. Its largest moon, Charon, was so big relative to Pluto itself that the two objects orbited a shared centre of gravity located in the space between them, a true binary system rather than a planet with a subordinate satellite. Everything about Pluto was strange when measured against the 8 planets, but that strangeness vanished the moment astronomers recognized the Kuiper Belt. Pluto was not a misfit planet. It was the largest known member of an entirely different population, the dominant resident of a frozen outer province that nobody had mapped. Its odd orbit, its icy composition, its small size, its binary companion, all of these features made perfect sense once Pluto was understood as a Kuiper Belt object, rather than as a failed planet. The reclassification in 2006, when the International Astronomical Union formally designated Pluto a dwarf planet, provoked public outrage that still echoes today. People felt that Pluto had been demoted, stripped of dignity, cast out of the planetary family. But the scientific reality was the opposite. Pluto was not demoted. It was promoted from the smallest, most marginal planet to the largest, most prominent resident of a vast outer territory. It went from being the runt at the end of the planetary line to the king of the Kuiper Belt. The reclassification did not diminish Pluto. It revealed its true context. The New Horizons spacecraft showed us what that context looks like up close. When the probe flew past Pluto on July 14, 2015, after a 9.5-year journey covering more than 3 billion miles, it carried humanity's first real look at the largest Kuiper Belt world. What it found demolished every expectation. For decades, Pluto had been a blur. Even the Hubble Space Telescope could resolve it as little more than a pixelated smudge, a few patches of light and dark, hinting at surface variation but revealing nothing specific. The working assumption among many planetary scientists was that Pluto would be a geologically dead ice ball, its surface cratered and ancient, frozen into inactivity billions of years ago by the merciless cold of the outer solar system. Small bodies far from the sun were not supposed to have interesting geology. They lacked the internal heat sources, tidal flexing from massive nearby planets, residual energy from formation, radioactive decay, sufficient to drive geological activity that kept worlds like Earth and Jupiter's moon Io alive. Pluto, at 40 times Earth's distance from the Sun, should have been a corpse. It was anything but. The first high-resolution images transmitted back to Earth revealed a world of shocking complexity. The most immediately striking feature was an enormous heart-shaped plain on Pluto's surface, informally named Tombor Regio after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. The left lobe of this heart, formerly designated Sputnik +NIH Shiar, turned out to be a vast basin roughly 600 miles across, filled with frozen nitrogen ice. Not water ice, which forms the bedrock of Pluto's crust, but nitrogen, a volatile substance that behaves like a slow-moving glacial fluid at Pluto's surface temperatures of roughly -230 degrees Celsius. Sputnik +NIH Shiar is not static. Its surface displays a remarkable polygonal pattern, irregular cells roughly 10 to 25 miles across, separated by shallow troughs. These polygons are the surface expression of convection. Heat from Pluto's interior, modest though it is, warms the nitrogen ice at the bottom of the basin just enough to make it buoyant. Warmer ice rises slowly toward the surface, spreads outward, cools, and sinks again along the cell boundaries. The entire basin is overturning in a process analogous to a pot of water heated gently from below, except the fluid is frozen nitrogen, and each convection cycle takes roughly 500,000 years to complete. The surface of Sputnik +NIH Shiar is being continuously renewed by this process, which explains its most astonishing characteristic: it has virtually no impact craters. In a solar system where every ancient surface is pockmarked by billions of years of bombardment, Sputnik +NIH Shiar is smooth. Its surface is geologically young, perhaps no more than 10 million years old, on a world 4.5 billion years into its existence. That youth means active processes are erasing craters faster than impacts can create them. Adjacent to the nitrogen plains, New Horizons revealed mountain ranges made of water ice. At Pluto's temperatures, water ice behaves like rock. It is rigid, strong, and capable of building towering structures. The Tenzing Montes and Hillary Montes, named after the first climbers to summit Mount Everest, rise as high as 20,000 feet above the surrounding terrain. These are not small bumps on an otherwise flat world. They are genuine mountains, comparable in height to significant ranges on Earth, built from ice so cold it might as well be granite. On the opposite side of Pluto from the gleaming heart, New Horizons photographed a vast dark region, informally called Cthulhu Macula, a band of reddish-brown material stretching nearly 2,000 miles along Pluto's equator. The dark colouring comes from tholins, complex organic molecules produced when ultraviolet light and cosmic rays break apart simple molecules like methane and nitrogen in Pluto's atmosphere. These fragments recombine into larger, darker compounds that slowly rain down onto the surface, staining it with the rusty hue of irradiated chemistry. Cthulhu Macula is ancient and heavily cratered, a stark contrast to the youthful Sputnik +NIH Shiar just a few hundred miles away. On a single world, Pluto displays both the oldest and the youngest surfaces found anywhere in the outer solar system. Then, there was the atmosphere. Pluto possesses a thin but genuine atmosphere composed primarily of nitrogen, with traces of methane and carbon monoxide. New Horizons photographed this atmosphere in spectacular backlit images as the spacecraft passed behind Pluto relative to the Sun, revealing more than 20 distinct haze layers, extending roughly 125 miles above the surface. These hazes are produced by photochemical reactions in the upper atmosphere, where ultraviolet sunlight breaks apart methane molecules, and the resulting fragments reassemble into heavier hydrocarbons that condense and settle downward as a fine organic mist. Pluto has weather. Nitrogen ice sublimates from sunlit regions, travels through the atmosphere, and refreezes on colder surfaces in a cycle that slowly reshapes the terrain over millions of years. On a world smaller than Earth's moon, orbiting in the deep freeze of the outer solar system, active atmospheric and glacial processes are reshaping the landscape in real time. New horizons also transformed our understanding of Charon, Pluto's largest moon. Charon is 750 miles across more than half Pluto's diameter, making the Pluto-Charon system the most extreme binary in the solar system relative to the sizes of its two members. Charon's surface revealed its own surprises. An enormous canyon system, stretching at least 1,000 miles long and reaching depths of 5 miles in places, cuts across the moon's equator. This canyon dwarfs the Grand Canyon and ranks among the largest chasms found anywhere in the outer solar system. Scientists believe it formed when Charon's interior froze and expanded, cracking the crust apart like an egg outgrowing its shell. The northern polar region of Charon is capped by a dark reddish stain that scientists have linked to methane gas escaping from Pluto's atmosphere, drifting across the gap between the two bodies and settling onto Charon's frigid pole, where ultraviolet radiation converts it into dark tholins. Pluto is painting its own moon. Beyond Charon, Pluto hosts 4 smaller moons: Nix, Hydra, Kerberos, and Styx, all tiny, irregularly shaped bodies orbiting in the outer reaches of the Pluto system. These moons are thought to have formed from debris generated during the giant impact that created Charon, making the entire Pluto system a product of ancient collision preserved in the deep freeze of the Kuiper Belt. None of this was predicted. None of it was expected. The scientific community had prepared itself for a dead world, and instead found a dynamic, geologically active, atmospherically complex planet-like body that challenged assumptions about what small, distant, cold worlds could do. Pluto is not just the largest Kuiper Belt object. It is proof that the frontier contains worlds as complex and as surprising as anything in the inner solar system, worlds that simply happen to operate on different timescales, with different materials, under conditions that the inner planets never experience. And that context was far richer than anyone had imagined. By the early 2000s, astronomers had begun finding Kuiper Belt objects that rivaled Pluto in size. These discoveries forced the reclassification debate and, more importantly, revealed that the frozen frontier was not populated solely by small anonymous chunks of ice. It contained genuine worlds, spherical bodies with complex surfaces, moons, and atmospheres. The first shock came in 2005, when the astronomer Mike Brown and his colleagues at the California Institute of Technology announced the discovery of Eris. This object, orbiting in the scattered disk far beyond the classical Kuiper Belt, turned out to be almost exactly Pluto's size, roughly 1,400 miles across, but noticeably more massive. Eris travels on a wildly elongated orbit that carries it from about 38 astronomical units at its closest approach to the Sun, out to nearly 98 astronomical units at its farthest point. Its orbital period is approximately 557 years. It is accompanied by a small moon named Dysno-Me-R. Eris was the discovery that broke the old definition of planet. If Pluto was a planet, then Eris had to be one too. It was more massive. And if both were planets, then what about the other large Kuiper Belt objects being found in rapid succession? The solar system could not keep adding planets every time a new icy body turned up beyond Neptune. Something had to give. What gave was the old classification system, and what emerged was the dwarf planet category, a recognition that the outer solar system contained a class of worlds too large to ignore but too numerous and too different from the 8 major planets to be lumped in with them. Makemake was the next revelation. Discovered by Mike Brown and his team in 2005 and announced alongside Eris, Makemake orbits in the classical Kuiper Belt at an average distance of about 45.4 astronomical units. It is roughly 890 miles across, making it one of the largest known Kuiper Belt objects. Its surface is extraordinarily bright and covered in frozen methane and nitrogen ices that should have been lost to space over billions of years unless some replenishing process keeps depositing fresh material. Makemake has at least one small moon, discovered in 2016, nicknamed MK2. The world is cold, distant, and strange, but it is unmistakably a world. It has geology. It has surface chemistry. It has a story written in ice. Haumea is perhaps the most bizarre of the dwarf planets. Also announced in 2005, Haumea orbits at about 43 astronomical units and belongs to the classical Kuiper Belt. What makes it extraordinary is its shape. Haumea is not spherical. It is elongated like an egg, stretched along one axis to roughly 1,400 miles, while measuring only 700 miles across its shortest dimension. This extreme shape results from an astonishingly fast rotation. Haumea spins once every 3.9 hours, one of the fastest rotation rates of any known large body in the solar system. The rapid spin has deformed it into an ellipsoid, a shape that would look profoundly alien compared to any world in the inner solar system. Haumea also has 2 small moons and a ring system, one of only a handful of small solar system bodies known to possess rings. Most remarkably, Haumea appears to be the parent body of a collisional family. A group of smaller Kuiper Belt objects shares similar orbits and surface compositions with Haumea, suggesting that a massive impact billions of years ago shattered part of the original body and scattered fragments into nearby orbits. This collisional family is the only one confirmed in the Kuiper Belt, a fingerprint of ancient violence preserved in the orbital architecture of the outer solar system. Then there is Quaoar. Discovered in 2002 by Chad Trujillo and Mike Brown, Quaoar orbits at approximately 44 astronomical units and measures around 700 miles across. Named after the creation deity of the Tongva people, indigenous to the Los Angeles Basin, Quaoar was one of the first large Kuiper Belt objects found after Pluto, and its discovery helped trigger the wave of large body detections that followed. In 2022 and 2023, astronomers made a startling finding. Quaoar possesses a ring system orbiting at an unusually large distance from the body. So far out, in fact, that classical physics struggles to explain why the ring material has not either collapsed into a moon or dispersed into space. The ring challenges existing models of how rings form and survive, adding yet another layer of strangeness to the frontier. Arrokoth rounds out the major dwarf planet candidates in the classical belt. Orbiting at about 39 astronomical units, Arrokoth is a Plutino, an object locked in the same 3:2 orbital resonance with Neptune that governs Pluto's path. Arrokoth is sometimes called the anti-Pluto because its orbit is almost a mirror image of Pluto's, reaching its farthest point from the Sun when Pluto is at its closest, and vice versa. Arrokoth is roughly 560 miles across and accompanied by a large moon named Vanth. Together, these bodies form yet another binary-like system in the Kuiper Belt, echoing the Pluto-Charon relationship on a smaller scale. Each of these worlds is a genuine place. Not a dot in a catalogue, not a smudge on a photographic plate, a place with a surface, a composition, a rotational period, a gravitational field, and in many cases, moons. The Kuiper Belt is not populated by anonymous rubble. It is populated by worlds cold and distant beyond ordinary human experience, but worlds nonetheless, and the named dwarf planets represent only the largest members of the community. Below them stretches a vast census of smaller bodies that astronomers have organized into distinct dynamical families based on how they orbit the Sun and how Neptune's gravity has shaped their paths. The cold, classical Kuiper Belt objects are the most ancient and undisturbed population. These bodies orbit between roughly 42 and 47 astronomical units on nearly circular paths with very low inclinations, typically less than 5 degrees off the ecliptic. They have not been significantly disturbed since the earliest era of the solar system. Their orbits are so calm, so circular, and so flat that astronomers believe they formed approximately where they are today, assembling gently from the original protoplanetary disk more than 4 billion years ago. Cold classicals tend to be redder in colour than other Kuiper Belt populations. They have higher albedos, and a remarkably large fraction of them exist as binary pairs, 2 objects orbiting each other as they jointly orbit the Sun. These binaries are fragile. Any strong gravitational encounter would have torn them apart. The fact that so many survive is powerful evidence that the cold classical belt has remained a quiet, protected neighborhood for the entire history of the solar system. The binary fraction among cold classical objects deserves particular attention because it tells us something that no other measurement can. Across the broader Kuiper Belt, roughly 5 to 10% of objects are known to exist as binary pairs, two bodies orbiting each other as they jointly orbit the Sun. But in the cold classical belt specifically, the binary fraction rises dramatically. Estimates, based on current surveys, suggest that 20 to 30% of cold classicals, and possibly more, are binaries. Some researchers believe the true fraction could be even higher, with many tight binaries remaining unresolved by current telescopes. These binaries are fragile. The gravitational bond holding two small icy bodies in mutual orbit is extremely weak. A single close encounter with a massive object, a passing Neptune scattered body, a gravitational perturbation from a nearby large Kuiper Belt object could easily tear a binary apart, sending its two components flying off on separate orbits. The fact that so many binaries have survived for over 4 billion years in the cold classical belt means that this region has experienced almost no significant gravitational disturbances over the entire history of the solar system. Nothing large has ploughed through. Nothing has stirred the population. The cold classical belt is the quietest dynamical neighborhood in the known solar system, and the survival of its binaries is the proof. This quietness carries a profound implication for the age of the material in the cold classical belt. If these objects have not been gravitationally disturbed, they have also not been thermally processed, collisionally resurfaced, or compositionally altered. They are pristine. Their surfaces record the chemistry of the original protoplanetary disk at the distances where they formed. Their shapes record the accretion processes that built them. Their colors uniformly red, distinctly different from the grayer hot classicals, and scattered disk objects reflect formation conditions specific to the cold outer disk, where different ice compositions and different organic chemistry dominated. When astronomers study the cold classical Kuiper Belt, they are not looking at objects that have been recycled, reprocessed, or rearranged. They are looking at material that has sat in the same orbital neighborhood, in the same physical condition, for longer than any surface feature on any planet. The cold classicals are the closest thing the solar system has to a time capsule that was sealed during the first 100 million years and has never been opened. The hot classical Kuiper Belt objects overlap in space with the cold classicals but differ sharply in orbital character. They travel on more eccentric orbits with higher inclinations, some tilted 20 or 30 degrees off the ecliptic. Their name does not refer to temperature. It refers to their dynamically excited orbits in physics. A hot population is one with high random velocities, analogous to molecules in a heated gas. These objects are thought to have formed closer to the Sun and been scattered outward during the giant planet's early migration, landing in the classical belt region but retaining the gravitational scars of their violent relocation. Hot classicals tend to be grayer and darker than their cold classical neighbors, a color difference that likely reflects different surface compositions and different formation environments. The Plutinos are Kuiper Belt objects trapped in a 3-to-2 mean motion resonance with Neptune. For every 3 orbits Neptune completes around the Sun, a Plutino completes exactly 2. Pluto is the most famous member of this group, but hundreds of other objects share the same resonance. The Plutinos orbit at an average distance of about 39.4 astronomical units, and their resonant lock with Neptune is not coincidental. It is a relic of Neptune's outward migration during the early solar system. As Neptune moved outward, its gravitational resonances swept through the primordial disk like a net, capturing objects and dragging them into lockstep orbits. The Plutinos are prisoners of that ancient sweep, still marching in time with their captor 4.5 billion years later. Other resonant populations exist at different orbital distances, each corresponding to a different integer ratio with Neptune's orbital period. The Twotinos, at approximately 48 astronomical units, orbit in a 2-to-1 resonance, 1 orbit for every 2 of Neptune's. Smaller populations occupy the 5-to-3, 7-to-4, and 5-to-2 resonances. Each group represents a different groove in the gravitational record, a different note in the symphony of Neptune's influence. Beyond the main belt lies the scattered disk, a more chaotic population of objects on highly elliptical and highly inclined orbits. These are bodies that ventured too close to Neptune at some point in their history and received powerful gravitational kicks that flung them onto wild trajectories. Some scattered disk objects travel from as close as 30 astronomical units to as far as several hundred astronomical units from the Sun in a single orbit. Their paths are unstable over long timescales, constantly being modified by gravitational interactions with Neptune. Eris, despite its size and prominence, is classified as a scattered disk object because of its elongated orbit. And then there are the extreme trans-Neptunian objects, the outermost members of this hierarchy, bodies like Sedna, that orbit so far from the Sun that even Neptune's gravity cannot easily explain their current trajectories. Sedna never approaches closer than 76 astronomical units, placing its entire orbit far beyond Neptune's direct gravitational reach. Something must have placed Sedna on such an extreme path, perhaps a passing star in the solar system's early history, perhaps an undiscovered massive planet, perhaps the gravitational influence of the Sun's original birth cluster. These extreme objects sit at the boundary between the Kuiper Belt and whatever lies beyond, hinting at gravitational forces that the current inventory of known planets cannot account for. Within the classical belt itself, astronomers have recently discovered even finer layers of structure. In 2011, a team of researchers identified a dense concentration of objects at approximately 44 astronomical units with unusually low eccentricities and inclinations. They called this concentration the kernel, a tight, ancient cluster that appeared to represent a particularly well-preserved fragment of the original protoplanetary disk. Then, in 2025, a clustering algorithm applied to orbital data of over 1,600 classical Kuiper Belt objects not only confirmed the kernel's existence, but identified a potential second structure, an inner kernel at approximately 43 astronomical units, characterized by an even narrower eccentricity distribution. This possible inner kernel, if confirmed by additional observations, would suggest that the cold classical belt preserves primordial structure at a level of detail that astronomers had not anticipated. The belt is not just old. It may contain fossilized architecture from the solar system's first few million years, preserved in orbital patterns like geological strata, frozen in stone. But the most dramatic evidence that the Kuiper Belt preserves ancient formation conditions came not from statistical analysis of orbits, but from a direct encounter with one of its smallest, most primitive residents. On January 1st, 2019, NASA's New Horizons spacecraft flew past a small Kuiper Belt object named Arrokoth, located approximately 44 astronomical units from the Sun in the cold classical belt. The encounter occurred 3.5 years after New Horizons' historic flyby of Pluto in July 2015, and it represented the most distant close-up exploration of any object in the history of spaceflight. What New Horizons found was unlike anything ever seen. Arrokoth is a contact binary, 2 distinct lobes joined at a narrow neck, giving it the appearance of a frozen snowman tumbling slowly through the outer dark. The larger lobe, called WEH-nu, measures roughly 12 miles across. The smaller lobe, WEO, is about 9 miles across. Together, the entire object spans approximately 21 miles from end to end. Both lobes are flattened, reddish in color, and remarkably smooth. The surface shows almost no craters compared to what scientists expected, suggesting that the environment in the cold classical belt has been extraordinarily calm. Few collisions, few disturbances, almost no violence for billions of years. The most important finding was how Arrokoth formed. The 2 lobes share nearly identical colors, compositions, and surface ages. They are aligned in a way that indicates they were once a co-orbiting binary pair that gradually spiraled inward and merged gently not through a catastrophic collision, but through a slow, delicate process of gravitational inspiral. The merger speed was likely no more than a few miles per hour. Walking speed. 2 small icy bodies drifting together in the outer solar system and touching so softly that neither one shattered, cracked, or significantly deformed. This gentle assembly is precisely what the streaming instability model of planetesimal formation predicts. In the early solar system, small particles of ice and dust in the protoplanetary disk concentrated into dense clumps through aerodynamic interactions with the surrounding gas. These clumps then collapsed under their own gravity, forming small bodies not through violent collisions but through collective gravitational settling. The objects that formed this way would have been born as binaries, or small clusters of components, gently aggregating into the shapes preserved today. Arrokoth is a fossil of that process. Its snowman shape, its gentle merger, its undisturbed surface, all of it records a moment in the solar system's earliest history when tiny building blocks of ice and rock were quietly assembling into the first solid bodies. And because Arrokoth sits in the cold classical belt, the most dynamically undisturbed region of the Kuiper Belt, it has been preserved in this primordial state for over 4.5 billion years. It is older than any surface feature on any planet. It is older than the craters on the Moon. It is a relic from before the solar system finished forming, sitting in the freezer of the outer dark, waiting to be found. Recent Hubble Space Telescope observations have reinforced this picture. In 2025, researchers studying the Kuiper Belt object Algira, a body in the same cold classical population as Arrokoth but roughly 10 times larger, found evidence suggesting it may be a triple system, 3 objects orbiting one another. If confirmed, this would be the second known triple system in the Kuiper Belt and would further support the streaming instability model, which naturally produces multi-body systems through gravitational collapse rather than collision. The emerging picture is that the cold classical Kuiper Belt is populated by gently assembled, often binary or multiple systems that have survived largely intact since the epoch of planet formation. The Kuiper Belt, then, is not a junkyard. It is not a heap of leftover scraps discarded after the planets finished forming. It is a province, a structured, populated, ancient territory where distinct neighborhoods preserve different chapters of the solar system's history. The cold classicals record the original disk. The hot classicals record the era of planetary migration. The Plutinos record Neptune's gravitational sweep. The scattered disk records chaotic encounters with the ice giant. The extreme trans-Neptunian objects record influences that may predate the solar system's current architecture entirely. Each population tells a different story, and together they compose a narrative far more detailed and far more revealing than anything the 8 planets alone can offer. The planets are the finished products. The Kuiper Belt is the archive of how those products were made, but an archive does not organize itself. The structure of the Kuiper Belt, its resonances, its distinct populations, its sharp boundaries, and its scattered outcasts, was created and is still maintained by a single dominant force. That force is Neptune, and the story of how one giant planet sculpted an entire outer frontier from a distance of billions of miles is essential to understanding why the invisible frontier beyond Neptune is anything but empty. Neptune does not simply border the Kuiper Belt, it rules it. From a distance of approximately 30 astronomical units, the 8th planet exerts a gravitational influence so pervasive and so precisely structured that it has organized an entire outer territory into distinct orbital families, carved sharp boundaries into the distribution of icy bodies, and maintained those patterns for over 4 billion years. Neptune is not a neighbor to the Kuiper Belt. It is the architect, the bouncer, and the warden, all operating simultaneously through nothing more than gravity extended across billions of miles of empty space. Understanding Neptune's role requires understanding orbital resonance, one of the most elegant and consequential phenomena in celestial mechanics. An orbital resonance occurs when 2 objects orbiting the same central body, in this case, the Sun, have orbital periods that form a simple integer ratio. This means the 2 objects regularly return to the same relative positions, and the small gravitational nudges they exchange at each encounter accumulate over time rather than cancelling out randomly. The effect is like pushing a child on a swing. If you push at the right moment in each cycle, even a tiny push adds energy consistently, and the swing climbs higher and higher. Push at random moments, and the energy input averages to nothing. Neptune's most famous resonance is the 3-to-2. For every 3 orbits Neptune completes around the Sun, objects caught in this resonance complete exactly 2. The Plutinos, including Pluto itself, occupy this gravitational groove at an average distance of roughly 39.4 astronomical units. The resonance is not a coincidence. It is a trap a gravitational cage that Neptune constructed as it migrated outward during the solar system's youth. The resonance protects its prisoners in a counterintuitive way. Pluto's orbit actually crosses inside Neptune's orbit during part of each cycle. If the two objects were orbiting independently, a collision or a catastrophic close encounter would be inevitable over billions of years, but the resonance prevents this. Every time Pluto approaches the point where it would be closest to Neptune, Neptune is always somewhere else along its own orbit. The timing is locked. Pluto and Neptune never get closer than about 17 astronomical units from each other, despite their paths physically intersecting. The resonance acts as a protective mechanism, ensuring that the Plutinos survive indefinitely in orbits that would otherwise be suicidally dangerous. Hundreds of Kuiper Belt objects share this 3-2 resonance with Pluto. They form a distinct population with specific orbital characteristics, semi-major axes clustered tightly around 39.4 astronomical units, eccentricities ranging from moderate to high, and a broad spread of inclinations. The Plutinos are not a random assortment. They are a dynamical family bound by a common gravitational relationship with Neptune. But the 3-2 resonance is only one groove in a much larger record. Neptune maintains resonances at multiple orbital distances, each corresponding to a different integer ratio. The 2-1 resonance at roughly 48 astronomical units traps objects called twotinos that complete one orbit for every two of Neptune's. The 5-3 resonance, the 7-4 resonance, and the 5-2 resonance each capture their own smaller populations at their respective distances. The 5-2 resonance, located at about 55 astronomical units, is particularly puzzling because it is a third-order resonance, weaker than the first-order resonances like 3-2 and 2-1, yet it appears to hold a surprisingly large population, comparable in number to the Plutinos. How so many objects became trapped in this relatively weak resonance remains an open question in solar system dynamics. Each resonance carves a signature into the Kuiper Belt structure. If you could plot the orbital distances of every known Kuiper Belt object on a single chart, the resonances would appear as vertical spikes, concentrations of objects at specific distances where Neptune's gravitational grooves trap material. Between the spikes, the distribution is smoother, populated by the classical belt objects that orbit freely without resonant entanglement. The overall pattern resembles a barcode distinct lines separated by broader bands, each line recording a specific relationship between Neptune and the bodies it governs. But why do these resonances exist at these particular distances? The answer reaches back to the most violent and transformative era in the solar system's history. The giant planets did not form where they orbit today. In the solar system's first few 100 million years, Jupiter, Saturn, Uranus, and Neptune occupied a more compact configuration, with Neptune likely orbiting much closer to the Sun, perhaps at 15 to 20 astronomical units rather than its current 30. Beyond the giant planets lay a massive disk of icy planetesimals, the raw material left over from planet formation, extending outward to perhaps 35 or 40 astronomical units. This disk contained many times more mass than the current Kuiper Belt, perhaps 30 to 50 Earth masses of frozen material. What happened next was catastrophic. The leading model for this transformation is called the Nice model, named after the city in France where it was developed by an international team of dynamicists including R. Les, R. H. N. Dro, Morbidelli, Harold Leveson, Rodney Gomez, and Cleomenis Tsiganis. First published in 2005, the Nice model proposes that the giant planet's orbits became unstable after several 100 million years of relative calm, triggering a sudden and violent reshuffling of the outer solar system. The instability was likely ignited by interactions between the giant planets and the outer planetesimal disk. As Jupiter and Saturn gradually exchanged angular momentum with the disk through gravitational encounters with individual planetesimals, their orbits shifted. At some point, Jupiter and Saturn crossed a critical orbital resonance with each other, likely the 2-1 resonance, and the resulting gravitational perturbation destabilized the orbits of Uranus and Neptune. The ice giants were thrown outward into the planetesimal disk. Neptune, in particular, surged from roughly 15 to 20 astronomical units all the way out to 30, ploughing through the dense disk of icy bodies like a gravitational snowplow. This migration was not a gentle drift. It was a violent, chaotic upheaval that reshaped the entire outer solar system in a geologically brief window of time, perhaps only 10 to 100 million years. As Neptune moved outward, its gravitational resonances swept outward with it, like the expanding ripples from a stone dropped into water. Each resonance, the 3 to 2, the 2 to 1, the 5 to 3, travelled through the disk at a specific rate, and any planetesimal that found itself at the right distance when a resonance passed through could be captured and dragged along. The chaos was not confined to the outer solar system. Neptune's migration and the broader giant planet instability unleashed a cascade of gravitational disruption that reached all the way into the inner solar system. As Neptune ploughed outward through the primordial disk, it scattered enormous numbers of icy planetesimals. Many were flung outward into the scattered disk or ejected from the solar system entirely. But a significant fraction was redirected inward, toward the orbits of Uranus, Saturn, and Jupiter. These inward scattered objects created a chain reaction. Each giant planet deflected some of the incoming material further inward while absorbing the rest. The net result was a surge of icy and rocky debris raining down on the inner solar system. Many researchers have connected this inward bombardment to a period of intense cratering recorded on the surfaces of the Moon, Mercury, and Mars. This era, known as the Late Heavy Bombardment, occurred roughly 3.8 to 4.1 billion years ago, several 100 million years after the planets themselves formed. The timing of the Late Heavy Bombardment has long puzzled scientists because impact rates should have declined smoothly after formation, not spiked hundreds of millions of years later. The giant planet instability described by the Nice model provides a natural explanation. The reshuffling of the outer solar system destabilized vast populations of small bodies, sending waves of impactors cascading inward on a timescale consistent with the Late Heavy Bombardment record. The Kuiper Belt's formation story is directly connected to the battered faces of the inner planets and the Moon. Even more provocatively, some of the icy material scattered inward during this upheaval may have contributed to Earth's water supply. The origin of Earth's oceans remains an active area of research. Earth formed in a region of the protoplanetary disk that was likely too hot for water ice to condense directly into the accreting planet. Some of our water must have been delivered after formation, carried by impacting bodies from cooler regions of the solar system. While carbonaceous asteroids from the outer asteroid belt are considered the primary delivery vehicles, icy planetesimals from the trans-Neptunian region, objects that would have become Kuiper Belt members had they not been scattered inward, may have contributed a measurable fraction. The isotopic ratios of hydrogen in Earth's ocean water are being compared with measurements of cometary water to test this hypothesis. If the connection holds, then some fraction of the water in every ocean, every river, and every glass you have ever held may trace its origin to the frozen outer disk that Neptune disrupted 4 billion years ago. The Kuiper Belt's formation did not only reshape the outer solar system, it may have helped make the inner solar system habitable. This is how the Plutinos were born. They were not placed in the 3 to 2 resonance by coincidence. They were swept up by Neptune's outward moving resonance and carried along as Neptune migrated to its final position. The resonance acted like a net, scooping objects from the original disk and depositing them at the distance where the resonance eventually stabilized. The same process populated the other resonances, each one capturing its own collection of icy bodies during the migration. Neptune's passage through the disk did more than populate resonances. It scattered enormous amounts of material. Objects that were not captured by resonances were instead flung onto chaotic orbits, some hurled inward toward the inner solar system, some thrown outward onto elongated paths that stretched far beyond the original disk. This scattering created the scattered disk population, the objects on wild, eccentric, highly inclined orbits that extend far beyond the classical belt. Every scattered disk object is a body that had a close gravitational encounter with Neptune at some point in the past and was violently redirected. The migration also explains the sharp outer edge of the classical Kuiper Belt. Observations show that the number of objects drops steeply beyond, about 48 astronomical units, near the location of Neptune's 2 to 1 resonance. Beyond this distance, the classical belt effectively ends. This cliff is not a natural feature of the original disk. It was carved by Neptune. As Neptune migrated outward, its 2-to-1 resonance swept to approximately 48 astronomical units and stopped when Neptune reached its final orbit. Material beyond this distance was never reached by the resonance and was not incorporated into the belt's resonance structure. Material inside was either captured or scattered. The result is a sharp truncation, an artificial boundary stamped onto the disk by Neptune's final position. The migration simultaneously explains the existence of the two classical belt populations. The cold classicals, the undisturbed, low-inclination, red objects on circular orbits between 42 and 47 astronomical units, are thought to be survivors. They formed in place within the original disk and managed to avoid being scattered or captured during Neptune's passage. Their calm orbits and pristine compositions reflect the fact that Neptune's migration was not perfectly efficient. Some regions of the disk were swept clean, others were left relatively untouched. The cold classicals occupy a narrow survival zone where the original disk material persists in something close to its primordial state. The hot classicals, by contrast, are immigrants. These objects originally formed closer to the Sun, perhaps in the region between 20 and 30 astronomical units, and were scattered outward during the giant planet instability. They landed in the classical belt region but retained the high eccentricities and inclinations characteristic of scattered populations. Their different colours and compositions support this interpretation. They formed in a warmer environment closer to the Sun, where the chemistry of the protoplanetary disk produced different surface materials. Neptune's gravitational influence does not stop at the edge of the classical belt. The scattered disk extends far beyond 50 astronomical units, and its most extreme members raise questions that Neptune alone cannot answer. Sedna, discovered in 2003, orbits the Sun on a path that never brings it closer than 76 astronomical units, more than twice Neptune's distance. At its farthest, Sedna reaches nearly 1,000 astronomical units into the outer dark. Its orbital period is approximately 11,400 years. Neptune's gravity is far too weak at Sedna's closest approach to have placed it on this orbit. Something else must have been responsible. The object designated 2012 VP113, discovered in 2012, has a similar detached orbit with a closest approach of 80 astronomical units. Another extreme body, 2015 TG387, comes no closer than 65 astronomical units. These objects share a puzzling characteristic. Their orbits are detached from Neptune's gravitational influence, yet they are not random. Their orbital orientations show suggestive clustering patterns that some researchers interpret as evidence of a gravitational shepherd, a large, undiscovered body whose gravity maintains the alignment. This is the Planet 9 hypothesis, proposed in 2016 by Konstantin Bartygin and Mike Brown at the California Institute of Technology. The Planet 9 hypothesis suggests that a planet roughly 5 to 10 times Earth's mass orbits the Sun at a distance of several hundred astronomical units, completing one orbit every 10,000 to 20,000 years. Such a planet, if it exists, would exert enough gravitational influence to sculpt the orbits of extreme trans-Neptunian objects into the patterns observed, explaining both their clustering and their detachment from Neptune. The hypothesis remains actively debated and is not confirmed. Some researchers argue that the observed clustering may result from observational biases, the tendency to discover objects in certain parts of the sky more easily than others, depending on where telescopes happen to point. A study published in 2021 by a team analysing survey biases found that the statistical significance of the clustering weakened when observational selection effects were carefully accounted for. However, it did not eliminate the possibility entirely. More recently, in September 2025, a team led by Amir Siraj at Princeton analysed the orbital planes of a large sample of Kuiper Belt objects and found that the average orbital plane of the belt is measurably tilted relative to the plane of the known planets. They proposed that this tilt could be caused by the gravitational influence of a massive body, at least 25 times Pluto's mass, residing within or near the Kuiper Belt. Whether this proposed body is the same as the Planet 9 predicted by Bartygin and Brown, a different and possibly closer object, or a statistical artifact remains an open question. The Planet 9 debate illustrates a broader truth about the Kuiper Belt. The frontier is not fully mapped. Its outermost reaches remain poorly surveyed, and the gravitational forces shaping its most distant members are not completely understood. The belt is a territory where confirmed observation, strong model-based interpretation, and genuine mystery coexist sometimes within the same dataset. What is confirmed, however, is that the Kuiper Belt extends farther than its traditional boundary at 50 astronomical units. In 2024, NASA's New Horizons spacecraft, now traveling through the outer reaches of the belt at distances beyond 58 astronomical units from the Sun, reported an unexpected finding from its onboard dust counter, the Venetia-Burney Student Dust Counter instrument. The detector was measuring higher concentrations of dust particles than models predicted for a region that was supposed to be beyond the belt's outer edge. Dust in the Kuiper Belt is generated primarily by collisions between larger objects. If dust levels remain elevated well beyond 50 astronomical units, it implies that a significant population of larger bodies must exist at those distances, producing the dust through ongoing collisions. This finding was corroborated by ground-based observations. A peer-reviewed study published in 2024 by the New Horizons Kuiper Belt search team, using data from the 8.2-meter Subaru telescope in Hawaii, reported the detection of an unexpected population of distant Kuiper Belt objects, stretching out to nearly 90 astronomical units from the Sun. These objects were found far beyond the traditional belt boundary, suggesting that the Kuiper Belt either extends much farther than previously thought, or that a second distinct belt of objects exists at greater distances. The dust counter finding deserves particular attention because of what it physically means. The Venetia-Burney Student Dust Counter aboard New Horizons is a small detector panel mounted on the exterior of the spacecraft. As New Horizons travels through space, tiny particles, some no larger than a few millionths of a meter, strike the panel, and the instrument records the impact. By counting impacts over time and knowing the spacecraft's speed, scientists can estimate the density of dust at various distances from the Sun. Models of the Kuiper Belt predicted that dust levels should peak somewhere around the belt's center, roughly 40 to 45 astronomical units, and then decline steadily as the spacecraft moved beyond the belt's outer boundary near 50 astronomical units. By 60 astronomical units, the dust density should have dropped to near background levels, the faint, uniform haze of interstellar particles drifting through the solar system from outside. That is not what happened. As New Horizons passed beyond 50 astronomical units, the dust counter continued registering elevated impact rates. The decline that models predicted did not materialize. At 55 astronomical units, dust levels remained higher than expected. At 58 astronomical units, farther from the Sun than Pluto ever travels on its orbit, the signal persisted. Something was producing dust out there. And the most straightforward explanation for dust production at those distances is collisions between larger bodies. Dust does not generate itself. It requires a population of bigger objects grinding against each other, chipping off fragments, producing the microscopic debris that the dust counter was detecting. This implied that a substantial population of Kuiper Belt objects exists beyond the traditional boundary objects that had never been individually detected by Earth-based telescopes, but whose collective presence was betrayed by the dust they produced through mutual collisions. The belt was not ending where it was supposed to end. Something continued beyond the boundary. The Subaru telescope detections reinforced this conclusion from a completely different angle. Rather than measuring dust, the Subaru survey directly imaged individual objects at extreme distances. The search team used deep exposures with a specialized wide-field camera to hunt for faint, slow-moving points of light in the regions of sky ahead of New Horizons' trajectory. What they found were objects at distances stretching toward 90 astronomical units, roughly 3 times Neptune's distance from the Sun. These were not scattered disk objects on elongated orbits that happened to be passing through the distant solar system. Their orbital characteristics suggested they belonged to a population residing at those distances, either as members of an unexpectedly extended classical belt or as constituents of a separate, previously unknown outer structure. The two discoveries elevated dust from the spacecraft, and direct imaging from the ground point toward the same conclusion from independent lines of evidence. The outer solar system contains more material at greater distances than any existing model of the Kuiper Belt predicted. Whether this material represents a smooth extension of the known belt, a distinct second belt, or something else entirely remains an open question that future surveys will need to resolve. If the belt truly extends to 90 astronomical units or beyond, its physical size would be staggering. The traditional belt spans from 30 to 50 astronomical units, a radial width of 20 astronomical units. An extended belt reaching 90 astronomical units would span 60 astronomical units of radial distance, tripling the known extent. The volume of space involved would increase enormously. The implications for the total mass and population of the outer solar system would require substantial revision of existing models. These discoveries connect to another critical function of the Kuiper Belt, its role as the source reservoir for short-period comets. The link between the Kuiper Belt and comets was the original theoretical motivation for predicting the belt's existence, and it remains one of its most important confirmed roles. Short-period comets, those with orbital periods less than 200 years, arrive in the inner solar system on low-inclination orbits, consistent with a disk-shaped source beyond Neptune. The mechanism is well understood. Neptune's gravity occasionally perturbs a Kuiper Belt object, particularly one in the scattered disk or near a resonance boundary, nudging it onto an orbit that carries it closer to the Sun. Once inside Neptune's orbit, the object falls under the gravitational influence of the other giant planets, which redirect it further inward through a series of gravitational encounters. Over thousands or millions of years, the object's orbit can evolve until it crosses the inner solar system, where solar heating transforms it into an active comet with a visible tail. The intermediate stage of this journey produces the Centaur's objects orbiting between Jupiter and Neptune on unstable paths that represent the transition between Kuiper Belt resident and inner solar system comet. Centaurs are escapees from the belt, objects that have begun the long gravitational cascade inward but have not yet reached the inner planets. Their orbits are chaotic, with typical dynamical lifetimes of only a few million years before they are either ejected from the solar system, destroyed by solar heating, or redirected back outward. The fact that centaurs exist today means they are being continually replenished from the belt. The Kuiper Belt is not a static reservoir. It is an active source, slowly leaking material into the inner solar system through Neptune's gravitational gateway. The centaurs deserve closer attention because they are the clearest physical evidence of this leaking process. Named after the mythological creatures that were half human and half horse, centaurs are objects that orbit the Sun between Jupiter and Neptune on paths that cross one or more giant planet orbits. They are hybrids, no longer Kuiper Belt residents, not yet inner solar system comets. Their orbits are inherently unstable, constantly being modified by gravitational encounters with the giant planets. A typical centaur survives on its current orbit for only a few million years before it is either ejected from the solar system entirely, redirected inward to become a short-period comet, or, occasionally, flung back outward toward the Kuiper Belt. Their lifespans as centaurs are cosmically brief, which means every single one visible today must have left the belt relatively recently. The most famous centaur is Chiron, discovered in 1977, orbiting between Saturn and Uranus. Chiron was initially classified as an asteroid, but later observations revealed that it periodically develops a coma, a fuzzy envelope of gas and dust, even at its enormous distance from the Sun. This coma indicated that volatile ices on Chiron's surface were sublimating, just as they do on comets much closer to the Sun. Chiron became one of the first objects to blur the boundary between asteroid and comet, and its discovery hinted at the existence of a transitional population between the Kuiper Belt and the inner solar system before the belt itself had even been confirmed. Other notable centaurs include Pholus, an extremely red object whose surface color suggests organic rich material preserved from the outer solar system, and Cari Clo, which in 2014 became the first small body in the solar system confirmed to possess a ring system, 2 narrow rings, orbiting this tiny object, roughly 190 miles across. The existence of rings around Cari Clo remains poorly understood. Rings typically require precise conditions to maintain themselves, and finding them around a small centaur on an unstable orbit was entirely unexpected. Astronomers estimate that the current Centaur population includes tens of thousands of objects larger than roughly half a mile across. Since their orbital lifetimes are measured in mere millions of years, the entire population must be continuously replenished. The Kuiper Belt is the reservoir. Neptune is the valve. When gravitational interactions nudge a Kuiper Belt object, typically one from the scattered disk, or from near a resonance boundary onto an orbit that brings it inside Neptune's distance from the Sun, that object becomes a centaur. From there, further encounters with the giant planets determine its fate. Some centaurs evolve inward over millions of years, their orbits gradually shrinking until they cross the inner solar system and begin outgassing as active comets. Others are ejected outward or destroyed. The pipeline from Kuiper Belt to Centaur to short-period comet is not a theoretical construction. It is an observed, ongoing process. Astronomers can track the orbital evolution of known centaurs forward and backward in time using computer simulations. These simulations consistently show centaurs arriving from the trans-Neptunian region and departing toward the inner planets. The connection between the frozen frontier and the comets visible from Earth is direct, physical, and continuous. Every short-period comet visible from Earth is a former Kuiper Belt resident. When you watch a comet cross the night sky, trailing a luminous tail of gas and dust, you are watching a piece of the frozen frontier that was dislodged from its ancient orbit and delivered to the inner solar system by the same gravitational machinery that sculpted the belt itself. The connection is direct and physical. The comets are messengers, fragments of the invisible frontier made temporarily visible by solar heat. Neptune's role in all of this is paradoxical. It is simultaneously the guardian and the destroyer of the Kuiper Belt. Its resonances protect certain populations, locking Plutinos into stable orbits that persist for billions of years. Its gravity carved the belt's structure, sorted its populations, and defined its boundaries. But Neptune also disrupts. It scatters objects onto chaotic orbits. It feeds the scattered disk. It ejects material from the belt entirely, sending it spiraling inward to become comets, or flinging it outward into interstellar space. Neptune is the force that created the Kuiper Belt's architecture, and the force that slowly erodes it, one gravitational encounter at a time. The belt we observe today is not the belt that originally existed. It is a remnant vastly depleted compared to the massive primordial disk that Neptune ploughed through 4 billion years ago. Estimates suggest that the original disk contained several hundred times more mass than the current belt. Neptune's migration scattered most of that material away. What survives is the fraction that was either captured into stable resonances, left undisturbed in the cold classical survival zone, or scattered onto orbits that happen to remain bound to the solar system. The Kuiper Belt is a ruin, magnificent in its extent but representing only a small fraction of the original outer disk. Yet even as a ruin, it is not dead. New Horizons dust measurements prove that collisions continue. Gravitational interactions with Neptune continue to perturb objects at resonance boundaries. The scattered disk continues to feed centaurs into the inner solar system. The belt is dynamically alive, slowly evolving, slowly losing material, slowly reshaping itself under forces that have operated continuously since the giant planets settled into their current orbits. And the belt story is about to enter a new chapter. The Vera Rubin Observatory, now operational in Chile with the largest digital camera ever built for astronomical survey work, is expected to discover approximately 35,000 new Kuiper Belt objects during its decade-long legacy survey of space and time, increasing the known population nearly tenfold. This flood of data will test every model of the belt's formation and structure. It will reveal whether the extended belt beyond 50 astronomical units is real and how far it reaches. It will provide the statistical power to determine whether the orbital clustering of extreme trans-Neptunian objects is genuine or an artifact. It will discover faint, distant objects that current surveys cannot detect, potentially revealing entirely new populations and structures. The frontier is not static. It is not a photograph frozen in time. It is a living, dynamical system, sculpted by Neptune, eroded by gravitational encounters, and still revealing new layers of complexity with every improvement in observational capability. What the Kuiper Belt has already shown us is remarkable. a structured outer province with distinct populations, ancient fossils, and a direct pipeline feeding comets into the inner solar system. What it is about to show us, as the next generation of telescopes comes online, may be even more transformative. But the deepest consequence of the Kuiper Belt is not found in its orbital mechanics or its population statistics. It is found in what the belt does to the human understanding of home. The Kuiper Belt does not merely extend the solar system, it fundamentally changes what the solar system means, and that change is the deepest part of this story. Ask someone to draw the solar system from memory. They will place the Sun at the center, then arrange 8 circles in order Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Some will add a ring around Saturn. A few might include the asteroid belt as a dotted band between Mars and Jupiter. Almost no one will draw anything beyond Neptune except possibly a small, wistful dot labelled Pluto, placed off to the side like a friend who was not invited to the reunion but showed up anyway. That drawing, which lives in the mind of nearly every educated person on the planet, is not wrong. But it is catastrophically incomplete, and the incompleteness is not a matter of missing a few small details. It is a matter of missing an entire outer province that changes the shape, the scale, and the emotional meaning of the solar system itself. The Kuiper Belt does not politely extend the solar system by adding a thin margin past Neptune. It transforms what the solar system fundamentally is. The familiar 8-planet arrangement, the model everyone carries in their heads, represents only the inner core of a much larger structure. Beyond Neptune, the solar system does not end. It opens into a vast, cold, ancient frontier populated by thousands of icy worlds, governed by gravitational resonances and stretching tens of billions of miles into darkness. Treating Neptune as the boundary is like treating the lobby of a cathedral as the entire building. The lobby is real, but the nave, the transepts, and the vaulted ceiling beyond it dwarf everything visible from the entrance. This is what makes the Kuiper Belt an invisible frontier. The word invisible does not mean undetectable. Astronomers have catalogued thousands of objects in the belt. Spacecraft have visited 2 of them. The belt is physically real, observationally confirmed, and scientifically well characterized. Its invisibility is not optical, it is psychological. The Kuiper Belt is invisible because the vast majority of people, including many who consider themselves scientifically literate, do not incorporate it into their mental model of the solar system. It remains outside the emotional map of home. This invisibility has deep roots. For most of human history, the outer boundary of the known solar system was defined by the farthest planet that had been discovered. For the ancient world, that boundary was Saturn, the slowest wanderer visible to the naked eye. When William Herschel discovered Uranus in 1781, the boundary doubled in distance overnight. When Johann Galle confirmed Neptune in 1846, based on mathematical predictions by Urbain Le Verrier, it pushed outward again. Each discovery extended the map, but the map always terminated at the last known planet. The edge of the solar system was wherever the outermost planet happened to be. This habit of treating the last planet as the finish line persisted even after Pluto's discovery in 1930. Pluto was treated as the final outpost, a lonely sentinel at the edge of everything for 6 decades. When the Kuiper Belt was confirmed in the early 1990s, the intellectual framework should have shifted. The solar system was no longer a sequence of planets ending at a final dot. It was a sequence of planets followed by an enormous structured region containing a fundamentally different kind of population. But the emotional adjustment never fully happened. The textbooks updated their footnotes, the diagrams added a few annotations, the fundamental mental image, 8 planets, then nothing barely changed. The resistance to incorporating the Kuiper Belt into the picture of home reflects something deeper than laziness or ignorance. It reflects a cognitive preference for tidiness. The 8-planet solar system is clean. It has a beginning, a middle, and an end. Each planet occupies a well-defined orbit. The inner rocky planets cluster near the Sun. The outer gas and ice giants spread farther out. The whole system fits on a single poster. It can be memorized by a child. It feels complete. The Kuiper Belt ruins this completeness. It introduces a region that is messier, less organized, and far harder to summarize. The belt contains multiple overlapping populations with different orbital characteristics, different formation histories, and different relationships to Neptune. It has no single representative object the way the inner solar system has Earth, or the outer system has Jupiter. Its boundaries are fuzzy. Its population is diverse. It resists the kind of clean categorization that makes the planetary system feel intellectually manageable. And this is precisely why the Kuiper Belt matters so much for understanding what the solar system really is. The neat 8-planet model is a simplification, a useful one, but a simplification nonetheless. The actual solar system is not neat. It is layered, complex, and structured at multiple scales. The Kuiper Belt is where that complexity becomes impossible to ignore. Beyond Neptune, the solar system stops behaving like a well-organized diagram and starts behaving like a wilderness, a structured wilderness with its own geography and its own rules, but a wilderness nonetheless. Consider the contrast in physical terms. The inner solar system, from the Sun to Mars, spans about 1.5 astronomical units. The outer solar system, from Jupiter to Neptune, spans roughly 25 astronomical units. The Kuiper Belt's main body, from 30 to 50 astronomical units, adds another 20. And the scattered disk and extreme trans-Neptunian objects extend the solar system's gravitationally bound population to hundreds of astronomical units. If recent discoveries of objects near 90 astronomical units prove to represent an extended belt, or a second belt beyond the classical boundary, the populated outer solar system could stretch 3 times farther than previously recognized. In terms of volume, the disproportion is even more extreme. Volume scales with the cube of distance. The region of space occupied by the 8 planets, from Mercury to Neptune, is enormous by human standards, but modest compared to the volume encompassed by the Kuiper Belt and scattered disk. The outer frontier occupies a shell of space vastly larger than the planetary core. Most of the solar system's physical volume lies beyond Neptune, in the cold outer regions where the belt and its associated populations reside. The planets are the dense, bright center. The Kuiper Belt is the sprawling outer territory, darker, colder, and far more extensive. Beyond the Kuiper Belt lies an even more extreme structure. The Oort cloud, first proposed by the Dutch astronomer Jan Oort in 1950, is a hypothetical spherical shell of icy bodies believed to surround the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units. Unlike the Kuiper Belt, which is a relatively flat disk aligned with the plane of the planets, the Oort cloud is spherical, a vast bubble of cometary nuclei enveloping the entire solar system in 3 dimensions. The Oort cloud has never been directly observed. No telescope has imaged an object confirmed to reside within it. Its existence is inferred from the orbits of long-period comets, which arrive from every direction and at every inclination, consistent with a spherical source. The cloud is believed to contain trillions of icy bodies, vastly outnumbering the Kuiper Belt population, but spread so thinly across such an immense volume that individual objects are separated by millions of miles. The Oort cloud's outer edge, at roughly 100,000 astronomical units, marks the approximate boundary of the Sun's gravitational dominance, the point where solar gravity becomes comparable to the gravitational pull of passing stars and the tidal forces of the Milky Way galaxy itself. Beyond this distance, objects are no longer bound to the Sun. They drift into interstellar space. If the Oort cloud represents the solar system's ultimate boundary, then the Kuiper Belt occupies a specific and important position within the hierarchy. It is the first transition zone, the place where the familiar, well-organized inner system gives way to something colder, less orderly, and profoundly less human in scale. The Kuiper Belt is not the edge. It is the threshold. It is the region where home begins to feel less like home and more like the boundary between the known and the unknown. This threshold character is what gives the Kuiper Belt its emotional weight. The planets, for all their diversity, feel comprehensible. We have sent spacecraft to all of them. We have mapped their surfaces, sampled their atmospheres, and studied their moons. They have names drawn from mythology and literature. They are characters in the human story of exploration. Even the most distant of them, Neptune, orbiting in cold blue isolation, feels like a known quantity, a place with an identity. The Kuiper Belt does not offer this familiarity. Its residents are not characters in the same narrative. They are members of a population anonymous by the thousands, individually faint, collectively vast. The dwarf planets have names and identities, but they are the exceptions. The overwhelming majority of Kuiper Belt objects are known only by provisional designations, strings of numbers and letters that convey orbital data, but nothing resembling personality. The belt is a demographic, not a cast of characters. It resists the storytelling instincts that make the inner solar system emotionally accessible, and yet this demographic is telling us something essential about where we live. The Kuiper Belt reveals that the solar system is not a compact arrangement of well-known worlds. It is a vast structure, with a bright, familiar interior and a dark, populated, poorly understood exterior. The frontier beyond Neptune contains more distinct objects than the entire planetary system. It preserves older material. It records more detailed information about the solar system's formation. In purely informational terms, the Kuiper Belt may be more scientifically valuable than the planets themselves because it is a less processed, less altered archive of primordial conditions. The New Horizons mission illustrated this with startling clarity. When the spacecraft flew past Pluto in July 2015, it revealed a world of staggering complexity: nitrogen glaciers, mountain ranges of water ice, a thin atmospheric haze, and a vast heart-shaped plain of frozen nitrogen spanning hundreds of miles. Pluto was not the dead, featureless ice ball that decades of low-resolution images had suggested. It was geologically active, atmospherically dynamic, and visually breathtaking. The frontier had a face, and it was beautiful. 3.5 years later, when New Horizons flew past Arrokoth in the cold classical belt, it revealed something equally profound, but entirely different. Where Pluto was a world transformed by internal heat and atmospheric processes, Arrokoth was a world untouched by almost anything. Its snowman shape, its smooth surface, its gentle formation history, all of it testified to a region of the solar system so quiet and so stable that objects could survive for 4.5 billion years in essentially their original condition. Arrokoth was not beautiful in the way Pluto was beautiful. It was beautiful the way a fossil is beautiful for what it preserves, for the depth of time it makes tangible. Together, Pluto and Arrokoth bracket the range of what the Kuiper Belt contains. At one extreme, dwarf planets large enough to sustain geological activity and atmospheric cycles. At the other, tiny primordial relics so undisturbed they record the era of planet formation itself. Between these extremes lies a continuum of objects spanning every size, every dynamical history, and every degree of preservation. The belt is not a single type of place. It is an entire outer territory with its own internal diversity. The Vera Rubin Observatory is about to crack this territory wide open. Its legacy survey of space and time, now underway from the summit of Cerro Pachon in Chile, will survey the sky with the largest digital camera ever built for ground-based astronomical observation. Over its 10-year primary mission, Rubin is expected to discover approximately 35,000 new Kuiper Belt objects, roughly 10 times the current known population. Most of these discoveries will come in the first year or two of data, arriving not as a trickle but as a torrent. This flood of discoveries will transform the Kuiper Belt from a partially surveyed frontier into a statistically robust population. For the first time, astronomers will have enough objects to map the belt's structure in fine detail, to identify subtle subpopulations, to trace the boundaries of resonances with precision, to test whether the extended belt beyond 50 astronomical units is real and how far it reaches. The survey will determine whether the orbital clustering of extreme trans-Neptunian objects is genuine or a product of observational bias. It will discover objects too faint and too distant for current telescopes, potentially revealing entirely new dynamical classes that no existing model predicts. If the results confirm the hints from New Horizons dust data and the Subaru telescope's distant detections, the Kuiper Belt could prove to be far larger than its traditional boundaries suggest. A belt extending to 90 or even 100 astronomical units would triple the known radial extent of the solar system's populated outer region. The implications for total mass, total population, and formation history would be substantial. The solar system's outer architecture might need to be redrawn from scratch, but even without these future discoveries, what the Kuiper Belt has already revealed is sufficient to force a fundamental reassessment of what the solar system is and what it means. The solar system is not 8 planets orbiting a star. It is a star surrounded by a compact inner system of 8 major planets, embedded within a far larger outer structure of icy bodies, organized into distinct dynamical populations by the gravitational influence of the outermost giant planet. The planets are the core. The Kuiper Belt is the first great outer layer. The scattered disk is the next. The Oort cloud, if it exists as theorized, is the final, most diffuse envelope. Each layer is larger, colder, darker, and less orderly than the one inside it. The solar system is not a diagram. It is an onion, each layer revealing a new scale and a new character when peeled back. This layered structure has a temporal dimension as well. The inner solar system has been heavily processed. Planetary surfaces have been resurfaced by volcanism, eroded by atmospheres, and bombarded by impacts. The geological record of the planets is incomplete, overwritten by billions of years of activity, but the outer layers preserve progressively older and less altered material. The cold, classical Kuiper Belt preserves material from the solar system's first 100 million years in virtually original condition. The Oort cloud, if it exists, may contain material ejected during the very earliest phase of giant planet formation. The farther you go from the Sun, the deeper you travel into the past. The outer solar system is a time machine, and the Kuiper Belt is the first stop. This is the deepest reason the Kuiper Belt matters. It is not simply that additional objects exist beyond Neptune. It is that those objects transform the solar system from a tidy arrangement of planets into a vast, layered, historically stratified structure that records the full arc of its own formation. The Kuiper Belt makes the solar system larger in extent, richer in population, and deeper in time. It makes home stranger, colder, and harder to hold together as a single coherent idea. There is something unsettling about this realization, and the unsettlement is itself meaningful. Humans want home to feel bounded. We want to know where it starts and where it ends. We want a map that fits in the mind. The 8-planet solar system provided that comfort. It was large but comprehensible. It had edges. The Kuiper Belt dissolves those edges. It reveals that the solar system does not stop at any clean boundary. It fades from rocky planets to gas giants to ice giants to icy dwarf planets to smaller and smaller frozen bodies to scattered remnants to, eventually, the impossibly thin and distant haze of the Oort cloud, which itself blends imperceptibly into interstellar space. There is no wall, there is no finish line, there is only a gradual transition from here to everywhere else, and the Kuiper Belt is where that transition begins. It is the place where the solar system stops pretending to be simple and starts revealing its true character, a character defined not by neat orbits and familiar names, but by deep, cold, vast distance and ancient ice. Voyager 1 and Voyager 2, launched in 1977, are now the most distant human-made objects in existence, traveling beyond 160 and 137 astronomical units from the Sun, respectively. They have crossed the heliopause, the boundary where the solar wind gives way to interstellar plasma, and are officially in interstellar space. But even at those tremendous distances, they have not escaped the solar system's gravitational influence. The Oort cloud, if it extends to 100,000 astronomical units, lies unfathomably far ahead. At their current speeds, the Voyagers would need roughly 30,000 years to pass through the Oort cloud entirely. The solar system is that large, and the Kuiper Belt, at 30 to 50 astronomical units, or perhaps 90, or perhaps farther, still represents only the first few steps of that immense outward journey. When you look at the night sky tonight and think about the solar system, try to hold all of this in your mind at once. Not just the 8 bright planets charted by centuries of observation, not just the Sun at the center and the familiar orbital paths, but the frozen province beyond Neptune, the thousands of icy worlds in their resonant grooves, the snowman-shaped fossils tumbling slowly through pristine darkness, the dwarf planets with their rings and moons and inexplicable geology, the scattered outcasts on their wild elliptical paths, the dust that New Horizons measured far beyond where the belt was supposed to end. Try to feel the scale. Try to sense the cold. The Kuiper Belt is the invisible frontier not because it cannot be seen, but because seeing it requires abandoning the comfortable map and accepting a less familiar one. The real solar system does not fade gently into emptiness after Neptune. It opens into a structured, ancient, and deeply strange outer territory that quietly rewrites the scale and the meaning of everything we call home. The frontier was always there. It was there when Clyde Tombaugh found Pluto in 1930 and did not know what he was looking at. It was there when short-period comets blazed across ancient skies, carrying fragments of the outer dark into the inner light. It was there when David Jewett and Jane Lu spent 5 years searching for something the rest of the world assumed did not exist. It was there when New Horizons crossed Neptune's orbit and kept flying, deeper into the cold, farther from everything familiar, heading toward a snowman made of ice, older than any planet. The frontier was invisible because we chose not to look, because looking meant admitting that the solar system is not the orderly place we memorized in school, because looking meant accepting that beyond the last comfortable landmark, beyond the last blue giant planet, home extends into a wilderness so vast and so cold that the human mind struggles to contain it. Now we have looked, and the solar system will never feel the same again. The invisible frontier beyond Neptune is not a footnote. It is not an appendix. It is not a curiosity for specialists. It is the first place where the familiar idea of home gives way to something colder, stranger, and far more magnificent. A structured outer province of our own solar system, hiding in plain darkness, waiting for humanity to finally accept that the map was never finished and that the real edge of home lies farther out than anyone dared to imagine.